Okay, so our first fundamental problem deals with a pair of pliers. Kind of fun. Okay. It's not too often we actually have an example of something real. Okay. So what we are trying to do, we're trying to find two things here. One is basically what's the squeezing force on B, and then what happens with the pin A. Okay. So in a pair of pliers or a pair of scissors, as you know, there's a hole. Okay, and that's where things pivot. Okay, so we want to kind of begin to think what are the stressors on that little component right there. Okay, so we've got two pieces. We've got the one on the bottom and then the one that's on top. Okay, now what I did was to just go ahead and draw the one on the bottom. Okay, and I tried to trace it. It didn't turn out that good, but it'll do. It's going to be just fine. Okay, so now let's put the forces on there. So I've got 100 Newton here. Okay, and that thing's 200. The line of action is 250 millimeters away from my pivot here. Okay, so that's kind of nice. That's the way they've given us that information is nice. Saves us a little bit of time. Okay, and then up here at B, okay, we are thinking about the jaws squeezing down this way from either side. Okay, but from the perspective of each piece, okay, the bottom one feels that little piece B pushing against it this way, and then the top piece feels it pushing from this way. So we've got a force over here like this, and this is B. Okay. And we've got a line of action here. And again, it tells us what our distance is away from our natural pivot point right there. Okay. So to figure out what B is, that's all we need to work with right there. Let me make a little space here. And let's crank this baby out because it's super easy. We're going to put our pivot point at A. All right, now we'll start with the 100 Newton force, and that's going to be negative. It's out there at a distance of 250 millimeters. Okay, and then B is positive, and it's out there a distance of 50 millimeters. Okay, 0.05 B equals 0. Okay. Now let me show you a trick. Okay, let's suppose we multiply the whole equation by 1,000. Then we just get this. Okay. So you can get away with that sometimes, and that's kind of nice when that happens for us there. But basically, I just changed the units on that, but the units are going to cancel out anyway. Whether you go with 0.25 or you turn it into 250 doesn't really matter. Either way, you're going to get that B is 500. Okay, so we've got 5 times as much force that we're able to apply to our component. Okay, and that's what we like about pliers, is they let us squeeze things really hard. Okay, now to get at A, what we have to do is think about the different parts, think about the different components for it. So I'm going to go AY here. Now I'm choosing down because both my other forces have upward bits to them. Okay. And then B's got a component to the left, so we're going to need a bit to the right to offset that. Okay. Now, once we have that, we can proceed as normal with our forces. Okay. So, whoa, that's way bigger than it needs to be. Okay, so if we look at the horizontal forces, all right, we're going to have minus bx plus AX equals 0. Okay, so AX is BX, and that's just going to be B times the cosine of 45. And once you run that math, what you're going to get is 353.6. Okay, 353.6. That is a 3, I promise. Looks like a goofy arrow, but it's supposed to be a 3. Okay, and then we're going to do the same thing vertically. Okay, with our vertical forces, we're going to have By up, and we've got our 100 Newton force up, and then we've got Ay going down. Okay, and By is just going to be B sine 45 plus 100 minus Ay equals 0, and Ay then turns out to be 453.6. Okay, now it actually asks for the magnitude of the resultant force for A. Okay, so that means we have to Pythagorize this baby. Okay, so A itself, looking at root 353.6 squared plus 453.6 squared. There you go. And what you get out of that is kind of interesting. You get 575.1. Okay. And what's interesting about that is it's bigger than our applied force, and it's bigger than the force at B. Okay. So that little pin really takes a lot of abuse. And that's why if you ever see an old pair of scissors or an old pair of pliers, okay, they're all like loose, okay, because there's so much stress going on that little component there. And then there's some additional moment going on inside in the Z direction, okay, because the two pieces are offset, okay, just a little bit. Let me kind of see if I can show you what I mean. So the bottom piece, so if I sort of turn, I got to turn this way for you. Okay, so the bottom piece is kind of like here, and the top piece is here, okay? And so if I turn that, and if I look with my eyeball from this direction, okay, we're going to have each piece is going to look like this. And then there's a pin in there like that, okay? And what that pin is going to experience is equal and opposite forces here of 575.1, okay, which is a lot of moment, okay? And so the way you have to build these things is you have to put something on the outside of this pin to hold it, okay? And so then whatever moment you're generating from the 575 Newton force, you have to generate that with the little end caps, okay? And they're even smaller. If they're twice as small, then you're going to end up with 1100 newtons of force. Anyway, so those little bits that hold it together are super important, okay? And if you get a cheap pair of pliers or a cheap pair of scissors, they just have a little flange on them, okay? And that flange wears out pretty quickly because of the tremendous stress that's on them there. Okay, anyway, there we go. There's that one. So let's get ready to do the next one.